Hey guys, how are you?
Not too
So
bad. How are you?
I finished grading your midterms. You guys can look at it. I have some comments, like on things you maybe did wrong. So if you go to the module for the week when you had an exam, the solutions should be posted for it. So I don't know, maybe, yeah, probably not gonna go over it, but do you guys have any questions and some problems from the midterm? How do you guys feel about it? So I
I don't
think,
have any questions about it. I think it was pretty good.
yeah, so like I got some emails asking about like if I'm going to curve the exam. I'm going to decide at the very end. If I do curve, I'm going to curve like the final four. So it's like B is like an average. But I think what I'll do is on the next midterm, I'll put like a extra credit problem or something. So if you didn't do very good on the first one, you can make up for it on the next one. So there'll be like definitely at least one extra credit problem on the next midterm. So hopefully that will help. All right. Switch. All right, so again, last time on Monday, yeah, I had some issues with my computer. So you guys go to the module for this week. For chapter 4.1, there should be a lecture uploaded. I don't think we really need to go over it again. Like it's really just kind of a review of what we did at the end of chapter 2. So we already talked about subspaces, right? We talked about null spaces, column spaces. So now we're kind of going back to it kind of in the context of kind of a general vector space. And when we talk about subspaces, those are going to be subspaces of vector spaces. So then, I'm going to try and do 4.2 and 4.3 today if I have enough time. But again, it's not really much new. We're just kind of redoing a lot of the same theorems, except the difference is now that we're talking about general vector spaces. So general vector spaces have to satisfy our vector space axiom. So that was in the previous lecture. Kind of subspaces follow the same rules, right? The zero vector has to be in a subspace, and then it has to be closed under addition and scalar multiplication. But the difference now is we're talking about general vector spaces. So our vectors don't have to be like vectors in Rn necessarily. They could be just general vectors in a vector space. They could be sequences, they could be functions or polynomials and things like that. So it's kind of more general and abstract vector spaces. Right, and in this class, when we generate subspaces, there will be like two basic ways to do it. We would either take sets of linear combinations of vectors, so we can generate subspaces basically by spans of some sets of vectors, right? And we kind of prove this in chapter 2, but we'll go over this proof again here. So we'll show that when I take a span of certain number of vectors, it would always be a subspace. And then another way to generate subspaces when we're actually looking at linear equations, right? So we talked about null space and column space. So we'll look again at those guys and see why they always generate a subspace also. All right, but first we'll review null space. Remember, for null space, if we do have a matrix A, right, the null space of a matrix A written by null A is a set of all solutions of the homogeneous linear equation. So if I have a homogeneous linear equation x equals to 0, null space is basically all of the vectors x in Rn, right, that are mapping to 0, right? So kind of null space is going to be a subspace of Rn, right? So if we're looking at A as a linear transformation, null space is going to be a subset or a subspace of Rn, right? And we have options for it, right? Our null space could contain some non-zero vectors, or sometimes null space can only contain a zero vector, right? Because if I have matrix A multiplied by a zero vector, it always will be a zero vector. So 0 is always going to be in the null space. right? But sometimes we may have more vectors than just 0 in the null space. Right, and we'll do some examples, right? If I take the linear system here, right, it's a homogeneous linear system, right? Because my vector B here is all zeros. I can write down my coefficient matrix, right? Just pulling out coefficients of all the different variables x, right? So if I want to find the null space of this, I know I'm using the definition, right? A null space of the solution set of the homogeneous equation. So I need to find the general solution of the homogeneous equation, and that will define my null space for me. Right? But one thing to note here, I have my matrix at 2 by 3, so it's not n by n, it's 2 by 3. So if I'm looking for the null space will be subset of the domain, right? So I would be multiplying a 3-component vector here on the right, following my matrix multiplication. So what I can start with is at least for myself, I know that I'm looking for vectors in R3, such that when I multiply matrix A to such vectors, I'm getting 0. So how do I do this? Well, I have to go back to what we did before, right? I have to go back to doing my row reduction, right? I'm forming my augmented matrix, right? A with the 0 vector. I am trying to bring it to some row echelon form, right? So I only need to do a couple row operations here, right? So I'm getting to row echelon form. I can see that I have 2 pivot columns, right? First and second. And then in the third column, I'm going to have a free variable, right? So I can basically solve for x1 and x2 in terms of x3. So x3 is going to be my free variable. So x3 can equal to alpha, which could be any real number. And then what I need to do is basically find the general solution to this homogeneous problem. So I need to go back into my system form. X3 is a free variable, so x3 is alpha, real number. And then all of the other guys I can express in terms of x3, right? So x2 plus 3 halves x3 equals to 0, or x2 equals to minus 3 half x3, which is alpha, from the second row. And then from the first row, right, x1 minus 3 x2 minus 2 x3 equals to 0, or x1 equals to 3 x2 plus 2 x3, which is alpha. Right, and then I can substitute my x2 in terms of alpha. So I basically have my x1, x2, and x3 all expressed in terms of my free variable x3, which equals to alpha real number. All right, and then if I put everything in my vector form, I remember when we were finding vector solutions to matrix equation systems, each one of the components has alpha in it, so I can factor it out, right? And this x equals to alpha multiplied by this vector with all constant components. Basically, every solution of the homogeneous system will be expressed in this form, right? Then since alpha is any real number, we know that basically what this says is that my solution set of the homogeneous equation is just the span of this one vector here. So I can say, well, the null space is the span of this one vector here, which I pull out from my general solution. So in this it's pretty much basically always the way that we're going to look for our null spaces. Like there isn't really a faster way. You really have to look for the general solution to homogeneous system, or for the solution set to the homogeneous system. Write this in this vector form, and see, what is the linear combination? Which vectors do I need to take to be able to express my solutions to the homogeneous problem? And so the null space would be the span of those vectors. So we we did this before, so it's more of a review, but it is important to be very comfortable with all of those concepts. And also we did sort of show this in chapter 2, right? But we'll go over this again. So we can always assume that the null space of the m by n matrix, so it doesn't have to be an n by n, right? The null space is always going to be a subspace of Rn, right? And again, I think your book doesn't use this notation, but if you're reading some things online and maybe some other books, so I mean, I'm kind of used to using this notation for subspace, kind of like the arrow with the little kind of element here. All right, so this just means subspace, right? If you're lazy and you don't want to write the word subspace, you can just use this symbol here. All right, so this is a subspace, not to be confused with, remember that symbol for a subset. But I mean, a subspace is going to be a subset, right? So we know that the null space of A is a subset of Rn because, right, we're basically taking vectors in Rn. But in order for a subset to also be a subspace, we also need three additional conditions, right? We need zero vector to be in null space. And we need null space to be closed under addition and scalar multiplication. So we need, if U and V belong to the null space of A, then necessarily U plus V also belongs to null space. And closed under scalar multiplication, if U belongs to null space of A, then we need to have some constant or scalar times U must also belong to null space of A. Right, so I mean, kind of those three, but really four, because you always have to check if it's a subset first. If all of those are satisfied, then this would show that null space is also a subset of Rn. That makes sense. So again, we'll prove this once, and then from then on, you can just assume that null spaces are always going to be subspaces of the domain of Rn. Right? Makes sense. So here it's not that hard to show, right? So we know zero belongs to null space because zero is always a solution of the homogeneous equation, right? A times zero will be equal to zero. Null space is closed under addition, right? If U is a null space and V is a null space, that means that it's a solution of homogeneous equation. U is a solution, V is a solution, so A times U is zero vector, A times V is zero vector. Does U plus V belong to null space also? Well, we can check, right? If I plug this in for X, so A times U plus V, we know that multiplication by a matrix is basically equivalent to a linear transformation. So A times the sum is the sum of, right? A times sum of U and V is A times U plus A times V. Or you can just look at it as a property of matrix multiplication, right? I can distribute a matrix to the sum of the two vectors. But over here, since U is in null space and V is in null space, both of those guys equal to zero, and zero plus zero is zero. So closed under addition, right? U plus V is in null space. And the third condition is it's closed under scalar multiplication. I mean, again, if U is in a null space, then A times U is zero. But if I substitute C, some scalar times U, A times some scalar times U, again, I can look at it as linear transformations of properties of matrix multiplication. I can always factor out the constants, right? So this would be C times AU, because U is in a null space. A times U is zero, constant times the zero vector is a zero vector. So some constant times U is also in a null space, right? Okay, so null space is a subset of Rn. The three conditions of the subspace are satisfied. So this shows that the null space is a subspace of Rn, subspace. And so we prove this once, and from here on, you can just assume whenever something is a null space, you don't have to prove that it is a subspace of Rn. We already showed this here, right, in the theorem. So you can use this in an example, right? So say I have an example here. So I have a set defined by vectors in R4 with basically vectors with four components, where components are related by, right, first component minus twice second component plus 5 times third component equals to the fourth component. And then another condition, right, the third component minus first equals to the second, right? And I want to know if H is a subspace of R4, right? So how do I do this? Well, a couple of ways, right? I could, I know it's a subset of R4 because, right, I'm taking vectors in R4. I could go through the three conditions, but I could also use my theorem that we did before, that the null space is a subset of Rn, right? But here, if you notice, if you use your conditions here, right, you can rewrite this as a system. And if you write the system in a matrix form, it's really a homogeneous system, right? Actually, guys, wait, my computer is about to lose power. Let me plug my computer in real quick. So basically, the conditions I have here for my set H here is equivalent to writing down a homogeneous system. So my A, B, C, and D components of X are really exactly the same as the condition for X to be a solution of the homogeneous system. So all of the elements in this H are going to be exactly the same as the elements in the null space of A. So H equals to the null space of A, just by construction here. And we already know that the null space is a subspace of R4. So you don't really have to check conditions anymore. Right? You can conclude that the set H is a subspace. But be careful with this because it's not always going to be the case. So I have an example here, something similar, right? I'm defining my subset of R4 as, vector with 4 components. And here I have my components related also by two equations that look very, very similar, except for instead of B, I have B plus 2 here. Right? So what does this change? If I rewrite this again as a system of equations, because both of those have to be satisfied, right? And I have 4 variables, A, B, C, and D. If I rewrite this as a matrix equation, there is a difference here. Instead of the 0 vector on the right-hand side, I have a non-zero vector on the right-hand side, right? So 0 and 2. So I can't use the fact that all of the X's and H are solutions of the homogeneous system anymore because they're not here. This is not a homogeneous system. All of the X's that belong to this subset H are solutions of the non-homogeneous system. So I can't use the fact that null space is a subspace of R4. But here I can also quickly conclude that H is not a subspace simply because in order for H to be a subspace, right, my kind of 3 conditions, like 0 has to be in a subspace. But over here, if I look at this, 0 is not a solution of this system, right? If I plug in all zeros here, matrix multiplied by all zeros would be 0, 0, but I have 0 and 2. So because 0 does not belong to each just cannot be a subspace. 0 always has to be in a subspace. Yeah. So again, it's kind of like to illustrate if I'm kind of defining some of those subsets of R4 by introducing some relationships between variables in the vector X, then be careful, it's only going to be a subspace if I'm basically defining a solution of the homogeneous system, right? Otherwise, you have to check all of the conditions. In this case, it's not a subspace because 0 is not in each. Right? Any questions so far? So the next example here. All right, so we're gonna still on null spaces. And you're gonna one thing to notice, so null space is defined implicitly, right? Remember when we're finding null spaces, I mean, there isn't really a way to, just by looking at this matrix, I can't immediately kind of tell you what the null space is based on the columns of A or rows of A, right? Like I can with the column space. What I would have to do in every time is to write down my matrix, row reduce it, and then kind of figure out the general solution for the homogeneous problem. So it's defined implicitly. It's defined implicitly by basically finding a solution of the homogeneous equation. So to find an explicit description, which would be this description here when I'm finding a general solution, this would be an explicit description for my null space. All right, and we can do one more example here for this. Right. All right, so if I have a matrix A, all right, I have a 3 by 1, 2, 3, 4, 5, 3 by 5 matrix. And if I want to find the null space, right, what is the null space? I mean, for one, I can note, well, what is null space is going to be a subspace of what, right? If this is a 3 by 5 matrix, my X that belongs to null space will belong to R5, right? Null space will be subspace of R5, right? And I have to look at, well, what is the general solution of the homogeneous problem? And again, you have to write down your augmented matrix, right, with 0 vector adjoint because I'm solving a homogeneous problem. You have to row reduce it, so include some work, right? So here's I already did the row reduction to echelon form. Once you do that, then you can look at what you have on your row echelon form. So you will have your pivots, right? Maybe you'll have some rows of all zeros. But you have to identify where are your pivot columns. So pivot here in the first column, pivot here in the third column. So first and third columns are my pivot columns. And then the remaining columns, remember 0 was my column that was adjoint when I'm solving my linear system, right? So it's good to like put the line some usually. Your book doesn't put the line, but I noticed in your exams, like some of you like start getting confused at the end, right? Because like this column does not belong to your matrix. You only have to look at the matrix A. And I mean, when you do this, you can also not even write the column of all zeros if you kind of keep in mind that they are all zeros. And you only really need this last column when you start solving for your variables in terms of other free variables. Right? But ultimately, I mean, you have your pivot columns, and then all the other columns that basically give you your free variables. So you have x2 from the second column, because I don't have a pivot, equals to alpha. You have fourth column, doesn't have a pivot. So I have a free variable x4 equals to beta. And the fifth column also doesn't have a pivot. So I have 3 variables here, alpha, beta, and gamma, corresponding to x2, x4, and x5. Now, and then all of the other variables, so x1 from the pivot column, the basic variable, and from the third column, x3, I can express in terms of my free variables, right? And then if I write down my vector form, right, so I'm basically writing my general solution of the homogeneous problem. My vector x with components x1 through x5, right, I'll copy down all of the relationships I got from my row echelon form or reduced row echelon form in this case. All right, I have my x1, x2, and then those are my free variables, alpha, beta, gamma. And then I'll just split everything apart, right, based on my alpha, beta, and gamma, right? So alpha multiplied by vector 2, 1, 0, 0, 0. Beta multiplied by 1, 0, minus 2, 1, 0, right? And gamma multiplied by minus 3, right? The 0, 2, 0, 1, right? So this is my solution that for homogeneous problem that's expressed in terms of my alpha, beta, and gamma, basically my weights corresponding to my free variables, right? So every solution in the set of solutions to the homogeneous equations can be expressed in this way, right? So my null space is basically the span of those three vectors, right? And also, I mean, we know that those three vectors will be linearly independent, right? So if I set this equal to 0, my weights corresponding to free variables will have to be equal to 0. And I mean, you can check if you set this equal to 0, right, then alpha, beta, and gamma will have to be equal to 0. So kind of by construction, this will be kind of the smallest possible set I can have to describe the null space. Right, so it's linearly independent. So I mean, for finding null spaces, I mean, there isn't really a shorter way to do it, right? You have to take your matrix, you have to row reduce it, you have to look at which ones are your free variables, express everything else in terms of free variables. And what you end up with is basically some linear combination of the number of vectors, where the number of vectors will correspond to the number of free variables. So number of free variables basically tells you the dimension of null space. It tells you how many vectors you will have in the basis of a null space. And so we'll talk about basis a little bit more too later, but we did talk about it in chapter 2.
Professor, I have a quick question. Can you reiterate or re-explain why the set of vectors written in this kind of more general form, why they would be linearly independent?
I mean, you can set them equal to 0, right? And you'll find that alpha, beta, and gamma will have to be equal to 0. Right, I mean, you can kind of do this from scratch. And you set this equal to 0, and so for alpha, beta, and gamma, they will have to be equal to 0. Right, or another way you can do it, you can basically start with u. Actually, it will be a little bit easier to get once we get to the so we'll do the basis theorem. Well, the spanning set theorem. So we'll have another theorem a little bit later, which actually explains this much better, right? But it will basically rely on the fact that if your set is linearly dependent, that means that you can basically keep going through your set until you get to the one vector that is a linear combination of the preceding ones. So in here, you can kind of start with one vector as linearly independent if it's not 0. Then if you go to the next vector, it will be linearly independent to this one. And then if you get to the next vector, you can show that it's linearly independent to the preceding two. Yeah, I think it would be kind of easier to, with the theorem, we'll do a little bit later. Yeah, but I mean, but for now you can just, I mean, if you set this equal to 0, I mean, how could you have non-zero alpha, beta, and gamma? Because I mean, those are free variables, right? And those vectors are not 0. Does that sort of make sense?
Oh, yes, thank you.
Kind of in other words, like if those vectors were linearly dependent, that means that you would be able to express one of them in terms of the other two, right? Say if the set was linearly dependent, then okay, maybe one of those vectors, maybe V could be expressed as a linear combination of U and W, right? But those guys are free variables, right? So they could be anything. So you can't really do it unless they're all 0. Right, so if you rewrote like, does that make sense?
Oh, yeah, no, that makes sense.
Yeah. But I think it will make more sense with like that, the theorem we'll do in a little bit, so. All right. Yeah, and maybe another way to look at it is, yeah, like if, I mean, this is the shortest way you can write the solution set. And if one of those vectors were a linear combination of the other two, then that would be even shorter way to write this, right? Because if this vector is a linear combination of the other two, then, I mean, I could basically write this as a span of just two vectors. But that's not possible because I know that this is kind of the shortest way to write the general solution. I have to use the three vectors. Kind of makes sense. You know, like the linear independence here really follows from the fact that I have three variables. All right, so like it has to be at least, there has to be three vectors and not less.
Would it also be an argument to if you took, say, two of the vectors and then set it equal, like their sum equal to the other one, and then tried to row reduce to see if it could be written as a linear combination? But if it couldn't, then you can then make the argument that it was linear independent. Is that
What do you mean? Yeah, I mean, you could rewrite this like, okay, if one of the vectors is a linear combination of the other two, I have to say, what if W equals to like some C1 times P plus C2 times W. Right. And then plug it in here and see why that doesn't work. I mean, I guess you could try doing that. But I think that the best way to look at it is just that this is this is the simplest way to express all of the general solutions, right, to the homogeneous problem. So if this was linearly dependent, that would mean that I could express like W in terms of V and U, right? Which would mean that I could actually express this as constant times one vector plus constant times other vectors. I could express everything in terms of just U and V, but I can't do that because I know that I have three free variables. So I need to have three arbitrary constants here. Does that make sense?
got it? Thank you so much.
Yeah, kind of like by contradiction, maybe we can do this. All right. So that's for node space. And then for column space, and also with this column space, but I'm kind of getting back to it and reviewing and maybe doing some more examples, but yeah. So the column space, remember, of the M by N matrix A is the set of all linear combinations of columns of A. So for column space, it's a little bit more straightforward, right? It's kind of defined explicitly. If I have a matrix A, like I don't necessarily even have to do anything to find the column space of A. All I'm doing is I'm taking the span of all of the columns of the matrix. You will have to do a little bit of work if you want to find the basis for the column space of A, because, right, if A does not span all of Rn or Rm, then maybe some of the columns would be linearly dependent, right? So you may have to reduce this set of all columns of A to a smaller set where the columns are linearly independent, right? But I mean, if you just want to know what the column space is, you can just take the span of all of the columns of A, right? So I mean, column space is basically just the range of the linear transformation defined by T, right? So column space is all of the vectors B in Rm such that B is 8 multiplied by some vector X in Rn, right? So it's the range of the transformation. And like, yeah, we've also in chapter 2, we proved that column space of A is the subspace of Rm. And again, it just follows from the fact that whenever I take a span of any number of vectors, it's always going to be a subspace, right? So we proved before that a span of any number of vectors that's closed under addition, scalar multiplication, and right, if I take weights as all zeros, it's going to be a zero vector. Right, so zero vector is in the span. And because column space is defined as the span of columns, then it's automatically going to be a subspace of Rm. Right. I guess we did this before. And I mean, we can do some examples, right? So, you know, I'm given W here. And I guess the question here is I want to find a matrix A so that the column space of A is given to me by the set W, right? Where I have three components, right? So I'm looking for a column space that is the subspace of R3. And my three components are related by those equations, right? So 6A minus BA plus B and minus 7A, where A and B are arbitrary numbers, right? So B is in W, then I guess I probably should have taken like B or something. All right, so vector V is in W, then vector V has this form. So I can just split this apart into vector components, right? So again, it's kind of like in a null space, right? I have two free variables here that could be anything. So if I split everything up, I'm just basically factoring out. I have a vector where I can factor out A and a vector where I can factor out B, right? So here the simplest representation for this would be linear combination of those two vectors, right? With A and B arbitrary real numbers. So W will be the span of those two vectors. And the simplest matrix A I can get from this is just take those two vectors and put them as columns in my matrix A. Because the kind of the subspace generated by a span of those two vectors, I can identify with kind of vectors being columns of the matrix A. And so then this subspace would be my column space, and this is my matrix A. Right. But again, here also, like those two guys are going to be linearly independent because I have to define my space or the span of those two vectors, right? Where A and B are any real numbers, so I have kind of like those two dimensions here. Right? If this was a multiple of the other one, then I would only have a one-dimensional subspace, but I know that I have a two-dimensional subspace. That makes sense? Right, I mean, this guy we also showed before, right? Kind of makes sense, right? The column space of an M by N matrix A is all of Rm if and only if our equation X equals to B has a solution for each B in Rm, right? So we kind of looked at it in the form of if I'm solving this, the system will be consistent, but you can also look at it in a form if I had a linear transformation that took X in Rn, so matrix multiplication AX equals to B. So if my column space is all of Rm, that means that my linear transformation is an onto transformation. It maps Rn onto Rm. Again, it's kind of review from what it before. I mean, the one thing we didn't do before is row space. So we didn't talk about row space. I mean, what is row space? It's like column space. I mean, I'm just taking, instead of columns, I'm taking rows of the matrix. Right, and then I'm taking the span of all of the rows of the matrix A. Right, so if matrix A is M by N, I will have M rows. Each row will have N components in it. So each row, if I'm taking it as a vector, is going to be a vector in Rn. Right? So I'm basically getting M Rn vectors in my row space. I mean, why we do row spaces? Well, I mean, we can always identify a row space of a matrix A with a column space of an A transpose matrix, right? So if I'm looking at matrix A and A transpose, the rows of A are columns of A transpose, right? So I can look at A transpose and find its column space, so I can look at A and find its row space. Right, so not really anything too new, but just, another way to represent something, right? So and we know that column space of A transpose, if A was M by N, right, then A transpose would be N by M. Now, so both of those are subspaces of Rn because they contain vectors in Rn. All right, and again, it's just basically taking a span of rows of A or taking a span of columns of A transpose, right? Of another object. But if you're just looking at row space of A, right, and you're not looking for like the smallest set that I can take to generate this, it's like for column space, you're just taking all of the columns, all of the rows in this case, and taking the span, and this would be a subspace. Subspace because every time I take a span of any number of vectors, it's always going to be a subspace. So kind of another thing we can define here. So we'll get back to how to get better representative sets for our subspaces, defining like row space, column space, node space, right? So how do we find bases? Like we would have to basically look at our matrix or our set of vectors and reduce it until all of the vectors are linearly independent. Because in this case, if I'm just taking all of the rows or all of the columns, that does not necessarily have to be linearly independent set. It's kind of more, we did most of this stuff before, right, in chapter 2. So if we look at linear transformations, kind of to recap for null space and column space. If we look at linear transformations defined by matrices, right, we're mapping Rn to Rm. If our matrix is M by N, null space will be a subspace of the domain Rn. Column space is basically the same as the image of the transformation, or it's a subspace of Rm, subspace of the codomain. Right? We have our definitions. Right? So, I mean, if we're working with column spaces, I can do one example here, kind of using this diagram. You have to be careful because if my matrix A is N by M, it's a square matrix. I mean, your null space and column space could be exactly the same, right? Or have a lot of the same elements. But if I am going from Rn to Rm, where N and M are different dimensions, then my null space is really completely different from the column space because, I mean, this lives in the world of Rn and column space lives in the world of Rm. Right, so they can't have any same elements. They're just logically different. They belong to different vector spaces, right? So if I have a matrix A here, 3 by 4, right? My M and N are not the same, not a square matrix. And if I have a vector, so if I wanted to check if this vector belongs to the column space, right? And if I want to check that this vector belongs to the null space, right? I know it does not belong to null space because null space is a subset of Rn. My n is 4. So null space subset of R4, but my vector v is a vector in R3, right? So my vector v definitely is not in a null space because, I mean, it's a vector with 3 components and null space has vectors with 4 components. But it could be in a column space. So to check if the vector is in the column space, what do? I mean, you can basically form your augmented matrix. Because if it's in a column space, it's basically asking a question, well, can V be expressed as the linear combination of columns of A, which is equivalent to asking, is augmented matrix system A with my vector V consistent, right? Do I have solutions for this? Do I have an X in Rn that basically generated my vector V when I multiplied that vector by A? So still kind of doing a lot of those row reduction problems. So if you row reduce it, you have your pivot columns. You notice that you have a pivot in every row. If you have a pivot in every row, that means that, I mean, yeah, your system is consistent and you will be in the column space. So again, here, like when you want to check if the vector is in the row, is in the column space or in the null space, I mean, first of all, look at, does your vector even belong to the embedding space, right? Does my vector here has 3 components? If I want to check if it belongs to null space or column space, I mean, I don't have to do anything for null space because this vector is not even the same dimension as vectors in a null space, right? But otherwise, you have to do your row reductions. It's the last things for this chapter. I should have an example here. Yes, first example. So if I have a square matrix on the other hand, right, then my matrix would be mapping vectors in Rn to vectors in Rn, right? So my column space and my null space are both subspaces of the same Rn, right? So column space of A is a subspace of Rn, and the null space is also a subspace of Rn. So vectors in column space and null space are kind of logically equivalent, they have the same number of components. So it makes sense to kind of ask more questions here. So if I'm given the column space of A equals to null space of A, so it kind of means that, you know, when I'm doing my linear transformation by multiplication of A, I mean, it doesn't mean they're the same, but it just means that kind of I'm mapping from the same subspaces, the same subspace. So this is my null space of A that maps to 0. Can we do it this way? Maps to 0. That is inside the embedding space Rn. And my column space is in the codomain Rn, but it contains the same similar types of vectors. So in here, it's kind of similar to one of your problems you had on the midterm. Remember, how the problem was like A squared, right? So I think some of you kind of got the idea and did it correctly. But here's how do I show this? So if the matrix, square matrix has column A equals to null space of A, and I want to show that null space of A squared equals to all of Rn. So if I start with X in Rn, right? So X in Rn is any vector X in Rn. Then A times X is going to be in the column space. Right, makes sense, right? I'm just taking A times X is all the linear combinations of columns of A. So it's going to be in the column space. But since column space equals to null space, if AX is in column space, AX is also in a null space of A. But if AX is in a null space, that means that AX is a solution of the homogeneous equation, right? Which means that if I plug in AX into A times AX equals to 0, this will be true, right? AX is a solution of the homogeneous problem. But then if I do a matrix multiplication, I'm getting that A squared times X equals to 0, right? So null space of A squared equals to Rn, right? Because X is any vector in Rn. And I'm showing that for any vector in Rn, A squared times that vector equals to 0, right? So null space of A squared is all of Rn. Does that make sense? So when you kind of like, when you had your, like example number 6, look at it a little bit. So I mean, you kind of have to do like some some preliminary work here, because in that exam problem number 6, you're given that I have a square matrix where columns are linearly independent, right? So you can do a little bit of work, like you weren't supposed to use the result of the invertible matrix theorem. Right? The point of that problem was to kind of like go through the reasoning again. Similar reasoning as in the theorem, but what was different here is that kind of now I'm dealing with a squared. You have to kind of like extend the concepts to a squared. But the idea was, okay, if the columns of A are linearly independent, right, we knew that AX equals to 0 has only the trivial solution, and A has n pivot position. And because A has n rows, A has a pivot in every row, which means that AX equals to B has at least one solution for each B, right? But our question was about A squared, just like in the previous problem here, right? So you have to kind of use what you have here and apply it maybe twice, a couple of times here. So if B is in Rn, then A squared x equals to B, I can rewrite as A applied to AX equals to B, right? And we know that the system A times something equals to B has at least one solution, right? So I'll call it U equals to AX, right? Because from the step. And then if I just look at AX equals to U, because I know that U will exist, I can apply this again and get that, well, this will also have at least one solution x belongs to Rn. Right, so A squared x equals to B has at least one solution x belongs to Rn. Yeah. But I saw, I mean, some of you, for the exam, I mean, some of you kind of followed the correct like logical steps, but I wanted to comment on this because I think only like one or two people even mentioned like A squared. So like you kind of have to look at your problem statement. I mean, there's a reason you're given like A squared here. All right, so just for the exam. But kind of one last little review thing. So I remember when you guys did linear transformation. Again, we're going to start looking at our vector spaces, subspaces, linear transformations, like null spaces, for more general vector spaces and subspaces, so not necessarily linear transformations defined by matrix multiplication, right? So we have to be able to use all those properties without kind of thinking of matrices A, m by n, right? But for general linear transformation, really the only thing that needs to be true is we're looking at linear transformations from a vector space to another vector space, right? So I have a vector space V and vector space W, right? Which do not in general have to be Rn and Rm. They're just general vector spaces. And then in order for T to be linear, I really just need to have those two conditions, right? Transformation of the sum of transformations for all vectors U and V in the vector space V. And then transformation of multiplication by a constant is constant times transformation, right? So I need to have those two conditions, then my transformation is linear. And notice, I mean, I'm not using anything about matrices here. The thing with matrices is because of matrix multiplication, how we define it, those conditions are automatically satisfied. So if transformation is defined by matrix multiplication, it will automatically be a linear transformation. But a linear transformation does not necessarily have to be defined by matrix multiplication. So I can define, I think we didn't define the kernel of T. So I mean, when we're dealing with matrices, we usually call null space like null space of the matrix A. But when we start dealing with more general linear transformation, I mean, sometimes you can kind of notation, you can refer to an equivalent of the null space of A as the kernel of T, right? The kernel of the linear transformation is basically all of the vectors X in the domain of the transformation that map to 0 in the range of the transformation. And I'm talking about it in general terms, right? And what was my column space of A for general linear transformation is the range of the linear transformation, which will always be a subspace of the codomain. And without using matrices, you can say that the range of T is all of the vectors B in the codomain such that linear transformation maps an X from the domain to that B. So it's basically range is kind of like the image of T. I had another word for it. So it's not always equal to W, which is codomain of T, but the range or image of T would always be a subspace of W, and the kernel of T or the null space of T is always going to be a subspace of the domain of T. All right, but for transformations, linear transformations that are defined by matrix multiplication, I can kind of summarize things that we know about this, right? So we know that the null space of A is only the zero vector, right? So only the zero vector maps to the zero vector if and only if linear transformation is 1-to-1, right? Or my homogeneous equation only has a trivial solution. And then for the column space, right, we know that the column space or image of A is going to be all of Rm if and only if linear transformation is onto, right? So onto means that we're covering all of the W with our image. And then 1-to-1 basically means that we're kind of mapping one unique vector to one unique vector from the domain to the codomain. Right, again, this is kind of recap what this is for. So I mean, we'll look at a lot of linear transformations that are not defined by matrices. And there's one classic example, but I mean, it kind of includes calculus. So you guys haven't done calculus, don't worry about it. But if you have done calculus, if you want an example of a linear transformation that's not necessarily a matrix, I mean, the operation of differentiation of a function is an example of a linear transformation, because remember, derivative of the sum is sum of derivatives, and derivative of multiplication by a constant, I can factor out multiplication by a constant. So I'm not gonna go too into it because I think we just already didn't do calculus yet, but there's a lot of linear transformations that are not defined by matrices. And so we'll do some a little bit later. Any questions so far? I think most of this is, we've done this in chapter 2, but in chapter 2, we've pretty much only looked at linear transformations defined by matrices, and we didn't really look at it in the context of kind of mapping a vector space to a vector space. So we also looked at the concept of linear independence of sets, and we looked at bases. And now we will look at it again, but again, we'll try not necessarily think of it in terms of kind of matrices or vectors in Rn or Rm, right? Because those concepts work for more general vectors that belong to vector spaces, right? So vectors do not have to be vectors in Rn, right? They could be polynomials, they could be continuous functions, they could be sequences, right? So vector space is not necessarily Rn, right? But all of those concepts of linear independence and what we did before still work here. So for general set of vectors in the vector space, we say that they're linearly independent, right? If I write down the linear combination of those vectors and set it equal to a zero vector, then all of the constants have to be equal to 0, right? So neither one of those vectors is a linear combination of the others. All the constants have to be equal to 0. And the set is linearly dependent if there is a non-trivial solution to this, right? So at least one of the C's is not 0, right? And if that is true, then kind of this relationship here with at least one of the c's not zero is our linear dependence relation. So in general, if the set is linearly dependent, you do need to outline, I mean, what is that linear dependence relation? Because, I mean, in practice, when you're dealing with those sets of vectors, you want to identify kind of the smallest subset of those, which is linearly independent. And a lot of the times you can use that linear dependence relationship in order to kind of figure out which vectors I need to toss away in order to be left with only linearly independent vectors. Right? So that linear dependence relation is important. Right? And kind of again, reviewing things for linear independence. If I only have a set of one vector, is linearly independent, right? Why? Because, you know, if I have one vector, C1 times V1 and set it equal to 0, then, I mean, C1 has to be equal to 0 if V1 is not 0. So it's linearly independent, unless V1 itself equals to 0. So the set that contains only the 0 vector is always going to be linearly dependent, right? Because, I mean, if C1 multiplied by 0 vector equals to 0 vector, C1 could be not 0, right? So linearly dependent. Then if I have a set of two vectors, I mean, all you have to do is just check if they're multiples of one another, right? If V1 is a multiple of the other, then they're linearly dependent. If they're not multiples of each other, then they're linearly independent. Right? So you don't have to do really that much work. Just check if they're multiples of one another. If the set contains more than two vectors, then you have to do a little bit more work. Then you have to solve kind of this linear dependence relation and see if my C1, C2, and CP all have to be equal to 0. Another thing to kind of be careful about, if I have a set of vectors and it contains a 0 vector in it, it's automatically going to be linearly dependent. I mean, why? Well, because when I write down my linear dependence relationship, the coefficient of 0 can be not 0, and I still get the 0 vector. So having a 0 vector in my set automatically makes the whole set linearly dependent. Right? So you don't want to have 0 vectors in your sets if you want a linearly independent set. And again, all of those things work for general vector spaces, right? Not just vectors in Rn, right? The V's could be like polynomials or functions or something else. Right? And then we'll have the theorem for vectors in Rn, but again, now we can kind of expand our field of view to all of the vector spaces, and we still have this theorem. Right? Remember that theorem said that in index set, if I have p vectors, where p is 2 or more, and my first vector is not a 0 vector, so I mean, it's kind of assuming you're taking sets of vectors that are not 0, because if I do have a 0, it's linearly dependent. This set is linearly dependent if and only if some vector in that sequence is a linear combination of the preceding vectors. So if you just read it in this form, it's kind of a little bit confusing, but really all it says is, I mean, if I have a set of vectors, so like V1, V2, Vj minus 1, Vj, and all the way to Vp. And I know that this set is linearly dependent. That means that I can basically keep going one by one in this set. So vector V1 by itself is linearly independent because one vector is always linearly independent if it's not 0. V2, if I take the set of two vectors, I can check, are they linearly independent or dependent? Say I checked, they're linearly independent, right? I add another one, independent. I add another one, independent. And I keep doing this until I get to some vector that when I add this additional vector, my set becomes linearly dependent, right? Because, once I start with the first vector, it's always independent. I mean, my vector that makes everything dependent could be the second vector. But the idea here is I start with the first one, it's independent, and then I keep adding, more and more and more to my new sequence until I add the vector that actually messes things up for me in terms of linear independence. Now, that's kind of the gist of this theorem. All right, so you can kind of keep increasing your set until you become linearly dependent. So it kind of says that, in a set of p vectors, if it's linearly dependent, it's basically like one of them or more that introduces this linear dependence to the whole other set, to the whole set. All right. And we can kind of look at it in terms of examples too. In general vector spaces, so say if my vector space is polynomial of degree at most 1, this is my V. And I'm taking the set of 3 different polynomials. P1 is 1, P2 is t, and P3 is 4 minus t, right? So if I just look at the set containing one polynomial 1, it's linearly independent, so it just has one vector. If I look at the set 1 and t, 2 polynomials, right? I mean, you can check this, right? If I do constant times 1 plus constant times t equals to 0, it's going to be linearly independent, right? Say a times 1 plus b times t equals to 0. I know that the only way for this to be equal to 0 is if a is 0 and b is 0. So it's linearly independent. But in this set, I have 3 vectors. 1 and t are linearly independent, but when I add a third vector, 4 minus t, that one is a linear combination of the preceding 2, right? Because my P3, which I added, is 4 times P1 minus P2, right? 4 times 1 minus 1 times t. So this one is a linear combination of the preceding 2. So this set is linearly dependent. I'm kind of looking at this theorem, sort of saying that my J here is 3, right? The first 2 were okay, but when I added the third one, that one made it linearly dependent, all right? So another example, also here, my vector space is the space of continuous functions on an interval from 0 to 1. All right, we kind of looked at this while this is a vector space. And I'm taking the set of sine and cosine, right? That set is linearly independent, because again, if you write down your linear dependence relation, like a times sine t plus b times cosine t equals to 0. The only way for this to be true is if a is 0 and b is 0, right? Or since this is a set of 2 vectors, is sine a multiple of cosine? No, right? There's no, I can't express sine as just a multiple of cosine. So they're linearly independent. So I can expand this set, sine, cosine, and sine t times cosine t. I mean, also, sine and cosine are linearly independent. This third vector, I mean, can I represent sine t, cosine t as a linear combination of just sine and cosine? And you can think of some trig identities, but I mean, yes, you generally can express sine times cosine in terms of sines and cosines, but your argument is going to be the same. So this is linearly independent to sine and cosine. Linearly independent, but say I add another function here, sine 2t, and this will be the one that makes everything linearly dependent, because now sine 2t, I can use identities and express it as 2 times sine t cosine t, but I already have sine t cosine t. So this fourth function is a multiple of the third function in my set. So this makes the whole set linearly dependent. Does that make sense? So I'm kind of going to get back to the concept that, the set of vectors is linearly dependent. It doesn't mean they're all kind of mutually linearly dependent. It just means that could mean that you just have one function that introduces this linear dependence. And in general, you can just kind of start from the beginning and go through your functions until you get to the one that is the multiple of the previous one. So it's the linear combination of the previous one. That makes sense? Any questions so far? So we kind of, I mean, we looked at this, we just mostly looked at the vectors in Rn. And here we're starting to look at more general vector spaces where I could have functions as my vectors and things like that. But we do kind of have to run through all of those concepts again. So bases, so we talked about bases for vector spaces in the context of Rn and Rm, but we also have bases for vector spaces and subspaces for general vector spaces and subspaces. So if H is the subspace of a vector space V, a basis for my subspace basically has two conditions that it has to satisfy. I mean, they have to be vectors in the embedding vector space V. And really what it has to be is it's kind of like the minimum spanning set for that subspace. So B has to be linearly independent and B has to span my subspace. So a spanning set that is linearly independent will automatically be a basis. Right, so I mean, why do we need this? Well, we need this to kind of find the most basic representation for our subspaces, right? So if I can express all of the elements in my subspace by just linear combination of 3 vectors, I mean, why take like 10 vectors, right? So we just want like the minimum number of vectors we need in order to write down elements of the subspace in terms of linear combinations. And that linear independence condition is basically what we need for that. Excellent. You can look at a couple examples here. And so if A n by n square matrix is invertible, right? A has n columns, and we know by invertible matrix theorem that if A is invertible, there's a lot of conditions hold. But in particular, what is true for invertible matrices is that all of the columns of the invertible matrix are going to be linearly independent, right? And if they're linearly independent, also we know that the columns will span Rn by invertible matrix theorem. Also, it's another condition that follows from invertible matrix theorem if A is invertible. So basically just A being invertible implies most of the conditions here. That means that the columns span Rn, and that means that the columns are linearly independent. So if I have n linearly independent vectors that span Rn, then this is going to be the basis for Rn. Right? So that's kind of an important example, because if you just know that the matrix A is invertible, you automatically know that the columns form the basis for Rn. It's pretty nice. I mean, another basis for Rn is the standard basis, which is basically the columns of my identity matrix N, right? So, I mean, you guys are familiar with those. You just basically have your vectors with 1 in every direction, depending on how many dimensions you have. So if you have like R3, you'll have 3 of them. It's the standard basis, but there is different ways to write the basis for Rn. It's just always going to have n vectors, and they always will be linearly independent, right? But that's for Rn. So we'll do maybe, maybe let's do this one first. Right. So something that's not an Rn. So if I take the set of monomials 1 t squared tm, right, and I'm looking at the vector space Pn, where Pn is basically all of the polynomials of degree at most n, right? So if P is in Pn, the general form is basically a polynomial with coefficients, right, a0, a1, all the way to n, and the power of monomials is up to n, right? So a0, a1, an could be any real numbers, right? So this is an example of a vector space also, right? Vector space of all polynomials of degree at most n, right? So if I want to find the basis for this vector space, I'm claiming that the basis for it would be just all of my monomials. And I mean, it's kind of intuitive here, right? Because, I mean, what are the elements of the vector space, which is polynomials here, that I need to use in order to generate all of the possible polynomials, right? And we kind of already wrote the elements of that vector space in terms of the linear combination of those guys, right? You know, my constants are those coefficients, right? So if I take S as 1t squared all the way to Tn, I know the span of S, right, all linear combination of those is going to be all of the polynomials. So the span of S is my vector space Tn. And then if I want to show that this is linearly independent, right, I mean here, if I set basically polynomial equal to 0, I mean, you can use like some ideas from algebra, right? But the fundamental theorem of algebra says that kind of polynomials of degree n can't have more than n zeros, right? And if it has more than n zeros, then it has to be the zero polynomial. And over here, I basically have a polynomial equals to a zero function, which has infinitely many zeros. So the only possible option for this polynomial is to be a zero polynomial, which means that all of those constants equal to 0, right? So because all of them equal to 0, then this shows that this set is linearly independent, right? Linearly independent spanning set is the basis for Pn, right? So here we have one example of a vector space that is not Rn, but we can use all the same ideas here, right? And we have spanning set that's the basis for Pn. Does that make sense? Yeah. Let's do this one example here. So let's have 3 vectors. I mean, those are vectors in R3. All right. So for R3, if I want to find out given 3 vectors, do those vectors form a basis in R3? So those 3 vectors are in R3. There's 3 of them, but they only form the basis for all of R3 if they're linearly independent. If they were linearly dependent, that means that they only span like a subspace of dimension 2 or dimension 1, right? So we really need to check that they're linearly independent. And when I'm checking if 3 vectors are linearly independent, I mean, unless it's obvious, some of them are multiples of another, you basically have to put them in the matrix format, because what we know about matrices, I mean, we kind of know a lot about matrices now, right? My sets of vectors are linearly independent if this matrix is invertible, or if this matrix corresponds to like an onto or a one-to-one linear transformation, or we can simply look at our pivot position, right? So if I put those 3 vectors into one matrix, row reduce it, and I see I have 3 pivot positions. So what does that tell me about my matrix? Well, a lot, right? I have linearly independent column, right? I have a unique solution for every B, right? All of those things. But it also tells me, I mean, what I need to know here, right? I'm looking at just are the columns linearly independent. And here, yeah, because I have 3 pivot positions in 3 by 3 matrix, the columns are linearly independent, right? So 3 linearly independent vectors in R3, they should form a basis for R3. Nice, but I'm gonna put those. We have time just to do this one theorem. right, which we a little bit talked about before in chapter 2, but we didn't really do this very rigorously. So, and this is a very important theorem, right? So it's called the spanning set theorem. And it kind of basically gives you some insight into how those spanning sets are generated. So if I have a set S of P vectors, so all of those vectors are in the vector space V. And I construct the subspace H by taking a span of those vectors, right? So again, H will automatically be a subspace because it's a span of vectors. So if one of the vectors in F, let me say VK or something, like one of the vectors in F is a linear combination of the remaining vectors in S, then the set formed by removing VK from S still spans H, right? So if one of the vectors in S is linearly dependent to the other one, if I just delete it from that set, I'm not changing the span of this set, right? And it's, I mean, pretty easy to see, right? So, I mean, whatever that one vector is, that is a collinear combination of the other one, you know, without loss of generality, you can say, well, maybe the last vector, right? If it's not the last, I can just rearrange terms, right? Because the order here doesn't really matter that much. So say maybe vector VP is a linear combination of the other vectors in this set, right? But my subspace is defined by the span of all of those, right? I mean, if I just take, if VP is a linear combination of the remaining vectors, I can write VP as a constant multiplied by all of the other vectors, all the way to VP minus 1, right? So one of the vectors is the linear combination of the others. Then if I take any H in this spanning set, I'm trying to prove that basically span of V1 through VP equals to span of V1 through VP minus 1, right? For any X in H, X can be expressed as linear combination of all of the V1 through VP. But since VP is a linear combination of all of the other vectors, if I plug it in here, I end up basically with having X equals to kind of addition of some constant multiplied by only V1 through VP minus 1. All right, so if I rearrange everything, X is basically a linear combination of vectors V1 through VP minus 1. All right, so VP being a linear combination of the other vectors basically deletes it from that spanning set. All right, so I can just take V1 through VP minus 1. So, and that's a pretty powerful concept because that gives us a kind of a framework for being able to find those sets that generate bases, right? If I start with a set that spans my subspace, those vectors may not all be linearly independent, but what I can do is kind of, you know, go through the set and keep deleting the vectors that make my set linearly dependent until my set becomes linearly independent. And in that case, it will be the basis for my subspace. And then the one other condition here from the spanning set theorem is, I mean, if H is not just a zero subspace, some subset of S is the basis for H. All right, so we can also kind of look at it. Why? And I mean, the main idea here again is if I take a set S of vectors in H that spans H, I'm basically just keep deleting vectors that make the set linearly dependent until the set becomes linearly independent. So kind of the more rigorously in steps, you can say, well, if S is linearly independent, then it's already a basis, right? If S is linearly dependent, then at least one of the vectors depends on others. So at least one of the vectors is a linear combination of others. So delete that vector, right? And then keep doing that. Keep deleting vectors that make things linearly dependent. Keep doing that until your set is linearly independent, and then that will be the basis. Or right? You can keep doing that until you have only one vector left, right? So then one vector is always linearly independent, and H is the span of that one vector. You have a basis. If that one vector is not equal to 0, it's okay. If that one vector equals to 0, well, you shouldn't kind of take 0 vectors in your set anyway. And the 0 vector you would have deleted when you were doing deletion of vectors that made everything linearly dependent. Does that make sense? Again, like the general idea of this is if I have any set of vectors in a vector space, and I generate subspace by taking the span of those vectors, then I can always kind of maybe reduce this set of vectors to a basis for that subspace, right? So some subset of this set S will always be a basis for H. Does that make sense? Yeah. Is there any questions? No, not too much. Too little, but I mean, I think as long as you understand things conceptually, like it helps a lot with a lot of those problems. Right? I mean, again, the idea here is I am able to keep reducing the set until everything is linearly independent by just deleting those redundant vectors that are linear combinations of the other vectors, because I mean, I don't really need to use them because they're just combinations of the other ones. All right. This, how much time do we have? Maybe. Maybe do it. No, not at 1:04. Oh, right, I guess we're 11, not just 10. You know, I don't have that much left for this chapter, but maybe I'll finish it next time. Yeah, I will finish this next time. All right, well, any questions on this or anything else?
Just to confirm the definition of basis,
Mm-hmm. Yeah,
it's
so-
just,
Mhm.
yeah, it would be just essentially cutting the set until the set is independent.
Yeah, so like the definition of the basis for a subspace, right? Basically, all you need the collection of vectors that span the subspace and also linearly independent, right? And in order to get it, if you just generated a set, if you just took any set of vectors and took their span, it's going to be a subspace. But I mean, you want to kind of reduce the number of vectors to the minimum number of, like you see, like for example, this one here, sine, cosine, sine t, cosine t, right?
Mhm.
If I took the span of that, this would be a subspace. But do I really need to take the span of all four? Not really, right? Because I mean, sine 2t is just 2 times sine t cosine t, and I already have that one here. So if I just delete that one, then sine, cosine, sine t, cosine t, everything that's in the span of those three, I can express in terms of those three. But everything that's in the span of those three is also in the span of those four, right? Like the span of those four functions equals to the span of those three functions. So why not just take those three? Does that make sense? So like sine, cosine, sine t, cosine t is going to be the basis for a subspace spanned by sine t, cosine t, sine t, cosine t, and sine 2t.
Yes, that makes sense, yes.
Yeah, so and like what that theorem really tells you is that whenever you have a subspace generated by the span of so many vectors, I mean, those vectors may already be a basis if they're linearly independent, but if they're not linearly independent, then you can just go through this process of like deleting the ones that introduce dependence until you get to the linearly independent set, and that would be your basis. Make
Alright.
sense?
Yeah, that makes sense. It's just interesting. It's very fascinating.
Yeah,
And
it's
when
some-
you said it's
Uh-huh.
a very core one, would you say this is something that we should absolutely like one of the few things that you absolutely should take on once the class is finished?
Yeah, that's gonna come back to you. Like if you take, I mean, I think probably all of the math classes you take from then on, it will come back in one form with the other. Like if you take differential equations, for example, it would really come back. Because when you write down like general solutions to differential equations, the partial differential equations, I mean, a lot of this will have to do with like general solutions, right? You have to write them down, like you.
That's why I recognize this. I have taken DFQs already, and that's why this is seeming familiar.
Yeah, like when you write down general solution, you have like, depending on the order, you have like C times one solution, C times another solutions, and those individual solutions have to be linearly independent, right? So it's the same concept here.
Oh, that makes it so much easier. Okay.
Yeah. Yeah, just think of your like, differential equations.
All right. Thank you, Professor. Have a great day. Enjoy your weekend.
Yeah, no problem. You too. So see you guys next time.